Hi and welcome to this inferential statistics video. So in this video we're going to revise the central limit theorem. So just a little note before revising this, it's really important that you've already revised your z-scores, as they're going to link a lot to our z-scores on page 36 and 37 in your log tables. So let's talk really quickly about populations and samples. So when we want to gather information, it's not always possible to work with the full population, and the population is the group that we want to know more information about. It can be very time consuming and expensive. So the alternative is to use a sample to work with that represents the population. Okay, but when we do this, the practicality of using a sample means that we cannot equate the results from a single sample with those from a population. So what that means is mu, the mean of our population, is not the same as x bar, the mean of our sample. So just because I take a sample, the sample does not exactly represent the population. It'll give us a good idea about it, and we can infer some information about the population using the information we have in the sample, but we cannot say that mu is equal to x bar, and that's really important. And when we use the central limit theorem, that's what we're going to be trying to overcome, this idea that mu does not equal x bar. Other ways that we've overcome this, if you've not already revised, is looking at using confidence interval, creating confidence interval, and those videos are all linked below. And there is a full inferential statistics video that goes through everything within the inferential statistics course. So just a quick reminder, mu is equal to the mean of the population, x bar is the mean of the sample. So we already know that mu is the mean of the population and x bar is the mean of the sample, but I'm going to give you two new words now. So mu is actually called a parameter and x bar is called a statistic. And what that means is a parameter is a numerical property of the population and a statistic is a number of property of a sample. So we have seen in mock questions where they've kind of pulled these wording around a parameter or a statistic, and just so you're aware of what they mean, there's our definition here. So a distribution of sample means, so different samples get different means, but the distribution of sample means is normal for a large sample size. So what that actually means is, imagine I take my population and I take loads and loads and loads of samples, and for each of my samples I record x bar. And if I start recording those x bars, what I should find is the bigger my sample gets, the more like the normal distribution that these sample means will act. So what I get is something like this. If I take a small number, it looks a bit all over the place, and then I look a slightly bigger number and a slightly bigger number again. And what you can see is as n gets bigger, that means that the actual distribution of sample means is looking more and more like the normal distribution. And this is what we call the central limit theorem. So I saw the central limit theorem described as this one, so I thought it was very nice. So it's called statistical magic, and that is what it is. And as we work through it, and you'll see what the central limit theorem allows us to do. It is a bit of statistical magic. So the central limit theorem states that if a random sample of size n is taken from any distribution, and that's important, any distribution with mean mu and standard deviation sigma, then, provided n is large enough, we can say that the x bar, so the distribution of sample means, is approximately normal with mean, mu, and standard deviation squared of sigma squared over n. So just to help you, what we get in this notation is mean and the standard deviation squared. Standard deviation squared is our variance. We don't really talk about variance at Leaving Cert higher level, so we can think of it just as standard deviation squared. And it's so important because in real life we don't always know the distribution of the population, and I suppose we focus so much on very basic distributions. If you think about what we know the normal distribution. We've talked about the normal distribution a lot. Other than that, we've really only talked about either skewed to the right and skewed to the left. They're the only distributions we've had. So it's really important that if we have a random population that has some distribution that we don't know, that we can use the idea that if n is big enough, that we can basically use the sample as being normal or approximately normal. And when we deal with normal distributions, it means we can work with our log table. So here it is again, and I just want to point out that sigma squared over n. I said that was standard deviation squared, but where is it coming from? And it's coming from our log tables, and you might recognize it. It's the standard error of the mean or the standard deviation of the sample means. It can be called either of those things, and it is that squared. So it is the standard deviation of the sample mean squared, and that gives me sigma squared all over n, and that's this part here. The second thing that I suppose to point out here is our last statement here, provided n is large enough. And that is kind of like a condition, but we need to look a bit more about that. So for most situations, n equal to 30 will be large enough, and that is, once the sample size is greater than or equal to 30, the sample can be treated as a normal distribution. So this means we can use page 36 and 37 in our log tables. So that's the page that we care about. So it doesn't matter what kind of distribution, it doesn't matter the distribution of the underlying population. Once I have a sample of 30 or more, I can use page 36, 37 for the sample. So our magic number is 30. So that is, when we say large enough, we're talking about the sample size of 30 or more, and it's really important that you have that in your head. So let's try an example. So we're going to work with the standard error of the means. So a light bulb manufacturer claims that the length of a life of its bulbs has a mean of 16. So when I work in a question, the first thing I'm going to do is read my question, and as I identify something, I will label it. So mean 16. Now note that they haven't said anything about a sample, so I'm just going to call that mu. It has a standard deviation of 3 months, so that is standard deviation sigma. And an independent research company tests the sample of 60 bulbs, so that's n. Calculate an appropriate value for the standard deviation of the sample means. So that there, standard deviation of the sample means, it is not the standard deviation of the sample, it's the standard deviation of the sample means, and what that means for us is the standard error, so look at the words, of the sample mean. So the only word that has changed there is they have changed the standard deviation. The word deviation has been updated to error. So that's all they're asking for in this case. So the deviation has changed to error. So what we're looking for is go back to page 34, and we have standard deviation of the sample. Standard deviation of the sample means standard deviation all over root n. So that is the standard error of the mean, or the standard deviation of the sample means, is 3 all over square root of 60. And we can simplify that. And the calculator will obviously rationalize the denominator, and that is approximately equal to 0.387. So if you ever see that idea of standard deviation of the sample means, and you're thinking, oh, but we were told that standard deviation is the same. Yes, it is. But the standard deviation of the sample means it's something very different. It's the standard error of the sample means. So if you've already revised hypothesis testing, you'll know that we can use z-scores, for example, to conduct hypothesis testing. So we're going to use our z-scores here, and it's the z-scores for a sample. So it's called a one sample z-test. And there's two things that appear in this formula that allow us to make the connection to a sample rather than just our normal population. And that is x bar, which means the mean of our sample, implying that there's a sample, and n, which is the number of things in the sample, our sample size, and that means that we are also talking about a sample. So this formula is at the very top of page 35. It's underneath hypothesis testing, and we are going to use this as we work with these central limit theorem questions. So the central limit theorem part is actually very small. It's going to very much link to the z-scores that we've already seen. Acme Confectionery has launched a new bar called Chocolate Crunch. The weight of these new bars are normally distributed with mean 4.64 grams and standard deviation 0.12 grams. So as I'm working through this, I'm underlying anything important. So my mean is given as mu, and my standard deviation is 0.12 grams. A sample of 10 bars. Okay, that's my n. I selected at random and find the probability that the mean weight is between this and this. Okay, so first thing I'm going to do is I'm going to write down the probability that the mean weight is between, so that's x bar, sits somewhere between these two. Now, this is linking to our central limit theorem. Can I state that the sample is normal? And just to highlight how many things are in my sample, we have 10 bars. So just as a reminder, we had, once the sample was big enough, any sample, regardless of its underlying distribution, would be normal. And that is if we had 30 or more in the sample. So if the sample size was 30 or more. Our sample size is only 10, so will I be able to use the normal distribution? And the answer is yes, I can, because this is a special case, because the underlying population, we were already told, is normally distributed. So the sample will be normally distributed regardless of sample size. And that's important. The central limit theorem is more important for us when we're dealing with populations where the distribution is not normal or not known. Then once the sample is 30 or more, we can assume, okay, the sample will be normally distributed. However, because we know in this question that the population is normally distributed, we can say for sure that even with a sample of 10 bars, it will also be normally distributed. So we can go straight to our z-score formula. And the z-score formula is z is equal to x bar minus mu all over standard deviation all over root n. X bar, we have 2. We have to do x bar equals 4.6. That'll be 1. And we'll do x bar equals 4.7. That's the other one. We have mu, which is equal to 4.64. We have standard deviation, sigma 0.12, and we have n is equal to 10. So that will remain constant. So z is equal to 4.6 minus 4.64 all over standard deviation 0.12 all over square root of n. This one here is going to be z is equal to 4.7 minus 4.64 all over 0.12 square root of 10, and we're going to get our two z-scores here. So when we plug those into the calculator, we should get this as minus 1.05. It goes 4 zeros, so we round to 2 decimal places, and this gives me 1.58. So really what we're trying to find, the probability that we have minus 1.05 is less than or equal to z is less than or equal to 1.58. Now, I'm very much a fan of drawing this out, get a sense of what's going on, your normal distribution. So just a rough sketch. So here's my normal distribution. We have here in the center, so here is about minus 1.05, and about here is 1.58, and we're trying to find this piece in the middle. So what we're going to do is we're going to get the probability that z is less than or equal to 1.58, but then we're going to take away this piece at the end, because I'm going all the way back to the left, so the probability that z is less than or equal to minus 1.05. Now, that won't work, so instead what we have to do, so this one's fine, sorry, it should be 5.8. This one's fine, and instead what we have to do is it's going to be 1 minus the probability that z is less than or equal to 1.05. So how we got that, I'll do a second sketch. So there's my minus 1.05. I'm trying to take that part away. I can't, so instead I move up to the other end, which is 1.05. I can't even work that out, but it's 1 minus the probability that z is less than or equal to 1.05. And that's where I got my answer down here. So we are able to look up the tables and work this out. So we're looking at page 36-37. I'm just going to draw a line down here so we can keep track of what we're doing. And we should get 0.9429 minus 1 minus 0.8531. You can put that straight into your calculator with the brackets as is. Make sure the brackets are like this, and we get 0.796, which is 79.6%. So that's how we would work with a sample, but knowing that the underlying population is normally distributed, we don't need to apply the central limit theorem. So let's look at another example. The sugar content per litre bottle of soft drink is known to be distributed with mean 5.8, there's my mu, and standard deviation 1.2. A sample of 900 bottles is taken at random and the sugar content of each bottle is measured. Estimate 3 decimal places the probability that the mean sugar content of the 900 bottles will be less than 585. So we're trying to figure out the probability that X bar will be less than 5.85. Now, it didn't tell us anything about the distribution of the population. So the sugar content per litre bottle of soft drink is known to be distributed. All that they told us is that mu is equal to 5.8, sigma is equal to 1.2. That's all we know. So the problem is it's not necessarily normally distributed. They didn't tell us it was, but they didn't tell us it wasn't. So because we have taken a sample of 900, using the central limit theorem, we can say, well, because that's much bigger than our 30. So remember, once we're 30 or more, we're fine. So it's much bigger than our sample size 30. That means we can say that this sample will be normally distributed. So that's the good news. And this means we can go to page 35 and use the formula at the top of page 35 for z-scores. So it is x bar minus mu all over sigma over root n, and that gives us 5.85 minus 5.8 all over 1.2 square root of 900, and that will give us our z-score of 1.25. So we're really trying to figure out the probability that, sorry, not x this time, the probability that z is less than 1.25. So that's actually a lovely straightforward one. I'm just going to sketch it out anyway. Here's 1.25 and we're trying to find out that it is less than. So we're looking all the way here to the left. So we can simply look up 1.25 in our log tables. So we should get 0.8944. So this equals 0.8944. So I would write that as 89.44%. They want that correct 3 decimal places. They didn't say in percentage, so we will give it in the form that they want. So it would simply be 894, which when we turn it to decimal, which will be 89.4%. So just make sure to do the rounding. So that was the 3 decimal places. So this little example is from the middle of a section B exam question from the actual Leaving Cert. So if it just seems a bit random, it's because there was obviously some questions before it and some questions after it. However, I suppose I just wanted you to see exactly how the central limit theorem could be asked on a paper. So it is known that data on farm size are not normally distributed. The research institute could take many large random samples of farm size and create a sampling distribution of the means of all the samples. Give one reason why they might do this. So this little part was worth 5 questions. But what they're basically asking us to link to is the central limit theorem, and we would talk about the central limit theorem stating. So the central limit theorem, and it's not like you need to recite it. It just means for the central limit theorem, what it says is, so for a large enough, and that's okay. So for a large enough, and remember n is greater than or equal to 30. sample, the distribution of sample means will be approximately normal. And I would definitely be using this, but this was not required. So sigma squared over n. So normally distributed mu sigma squared over n. So from the marking scheme on this, it just basically said the distribution of sample means will be normally distributed. So they just wanted that, and you were definitely going to get your 5 marks for just that. However, we won't always be that lucky, so it is important that you have a better understanding than just learning off that one line. So that's how they have in the past asked that question. So that question came from 2016. And it was, like I said, a part of a much, much larger question. So it's 5 marks out of 50 in the whole question. It did a little bit of normal statistics with z-scores, and then it got into a bit of inferential. So this was its link between it. So this example, we're going to look at non-normal distributions. And this is from the exam paper in 2012. It's just part of a question. And just to note that in 2012, that was before the new inferential statistics was added. So it was added in 2015. So it is not maybe a traditional inferential like we would, but it is a nice question to link the idea of non-normal distributions, how we work with it, and then linking it to the central limit theorem. So they've been very clear here that this is not a normal distribution. When you look at this, you should be able to very clearly see that it's skewed to the right, or positively skewed, and they actually told us that as well. So let's read through the question. The distribution of hourly earnings for all employees in Ireland in 2009 is shown in the diagram. It can be seen that the distribution is positively skewed, with mu mean equal to 22.05, median is 17.82, we don't have a symbol for that, standard deviation of 10.64, lower quartiles, that's Q1, and upper quartile, that is Q3. Well, actually, we'll go with Q2 then for median. So that's where everything is. So definitely not normal, cannot do anything with regards to normal distribution, cannot use z-scores, anything like that. So we have to work with it as is. So let's look at what the question is asking us. If 6 employees are selected at random from this population, what's the probability that exactly 4 of them had hourly earnings more than 1280? Okay, so hopefully at this point when you see this kind of style question, Bernoulli should come to mind, because I have 6 employees and I want to find the probability that exactly 4, but I don't know which 4, and that's important. The order we don't know. So we'll have n equals 6 or equals 4 and the p. So this is the fun part. So they want us to find 4 of them had hourly earnings more than 1280. So what's the probability of having hourly earnings more than 1280? Well, notice here, and I'll actually use my highlighter so we can see it. It is the lower quartile. So that means the lowest 25%, they're the ones who earn 1280. So at that point there. So that's the point where there's a quarter lower but 3/4 higher. So probability of earning more than 1280 would be 75% or 0.75. because that is linked to the idea of Q1, so the lower quartile. So think of that drawn out here for a second. So there's the middle, there's Q2, there's Q1, and there's Q3. So we're dealing with this section here. So that's 1280. And I want to find out, well, how many have more than 1280? And you say, well, because here, that's the quartile, that's 25%, and that's 25%, and this is 25%. And 25%, so the bit I've highlighted in yellow must be 75%. So this gives me a probability of 0.75 and Q is equal to 0.25. So Bernoulli is n choose or, p to the power of or, q to the power of n minus or. We only have to do 4. Watch out for words like at least or at most, where you might have to do it a few times. Here we just have exactly 4. So we have 6 choose 4, 0.75, and you could put that in a fraction either if you prefer. I prefer working in decimals when we're dealing with nice decimals, but if you prefer to write 3/4 and 1/4, that's absolutely perfect. And n minus or is 2, and putting that into your calculator, we'll get our answer, and that is 0.296625. Okay. So the second part of this question, I've left the top part there because it's important. So in a computer simulation, I'm starting from here, the top part has not changed. So in a computer simulation, random samples of size 200, so I'm always on the lookout for things to label. So size 200 are repeatedly selected from this population, and the mean of each sample is recorded. 1,000 such sample means are recorded. So each sample is n, and there are 1,000 sample means. Okay, so there are random samples of size n and 1,000 such samples. That's important. Describe the expected distribution of these sample means, and your description should refer to the shape of the distribution and to its mean and to its standard deviation. So this is the part that's linking to the central limit theorem. So the central limit theorem, just as a reminder, says that the sample means will be approximately normal with mean mu and standard deviation sigma over root n. So let's look at this. So my sample means are going to be approximately normal with mu equal to mu, and remember mu up above here is 22.05, and now I'll have to do a little bit of work here. So standard deviation is the standard error of the mean of the sample mean squared. So I'm going to have my standard deviation, which is 10.64, all over n, which is 200. And I want to do this top bit squared. So when I work through that, I should get my standard deviation, or the standard error sample means, is about 0.752, but that's all squared, and that gives me 0.5655. So that gives me 0.5655, and just to remind you, that is my mean, and that is my standard deviation squared. So my standard deviation, because they did ask for that, is 0.752. Okay, so your description should refer to the shape of the distribution. So this is all a bit of working, we don't need this. And it's normal. And it has mean 22.05 and standard deviation 0.752. But we write that in terms of our normal distribution with mean and standard deviation squared. So the third part of this question, again, I've kept up the information from the start, and I've also added in 2 new pieces that we got the last time, and that was that we have a sample size of 200 and there was 1,000 samples. So how many of the sample means would you expect to be greater than 23? So first thing we're going to do is let's find the probability that the sample mean would be greater than 23. And I can't work with sample means, I can't work with x bar, so instead I'm going to work with z-scores, which means I'm going to convert. So what I use is on the top of page 35, we have the formula x bar minus mu sigma over root n. So just to make a note of what we have, my mu is 22.05. My x bar in this case is 23. My standard deviation is 10.64, and my n is 200. So putting that all into the formula, I get 23 minus 22.05 all over 10.64 over the square root of 200. And that gives me 1.26. So what I'm trying to do is the probability that z is greater than 1.26. So with regards our normal distribution, let's just sketch this out for a second. There's 1.26. I'm trying to find that it's bigger than that. I can't work to the right with my log tables, so I'm on page 36 of my log tables. So instead I say this is the same as 1 minus the probability z is less than or equal to 1.26. So when I work that out, I get 1 minus 0.8762. That's directly from my tables. And that gives me 0.1238, which is about 12.38%.